Now let us look at what is the Mips floating point support. So early days, floating point support in the program is used to be through a software libraries. Like so, processor as a hardware provides all the integer arithmetics and logical function. Only the software use those logics and those arithmetics, integer arithmetics. It makes those soft like algorithm. It implements the algorithm for floating point representation and corresponding arithmetic. Okay, it's usually like, for example, math.h, lip math. You link to them and stuff like that. Now, many of the common functions like addition, subtraction, etc., now are moved in the hardware, but in a separate processor. It's called a coprocessor in the system. For the Mars, you will probably notice that there is a coprocessor 1, okay, which is a floating point processor and associated with the Mips main general purpose processor. So, what's in a nutshell? In the older days, it was done all the way through the software libraries. There is no hardware support for directly computing or crunching floating point representation for different arithmetic function. But since then, in modern days, since technology has evolved, we can push more and more functionality onto the hardware. Common functions are mapped into the hardware, and so that your system, just like you do an integer arithmetic operation through the hardware, it does also arithmetic operation on the floating point values directly through the hardware, and they call it a coprocessor. Now, depending on the system, coprocessor can accommodate different sets of floating point math function. Simplest, of course, is add, sub, multiv, comparison, branching, etc. Complex one like a GPU is basically floating point, graphics, matrix processing kind of thing. There's highly advanced stuff nowadays going on. But let's stick to the Mips. Now, there are two varieties of math function, a single precision and a double precision. Okay, so anything extended with a .s in the instruction mnemonics is a single precision value, single precision operation, and anything extended with a .d is a double precision. So you will see something like instruction like add.s, add.d. So this is single precision add, this is double precision add. Similarly, sub s, sub d, multi-s, multi, etc. And comparison also has an S and D extension. So there in general is called a C dot something dot S. What it means? C stands for comparison, S stands for single precision, and D stands for double precision, where X is equal, not equal, LT, less than, equal, greater than equal, etc. So you will see some instruction like C dot EQ dot S means is a comparison equal operation on the single precision, and if you see C dot equal dot EQ dot D, which means the equality comparison for the double precision. Similarly, you can see some instruction like C dot LT dot S or C dot LT dot D, etc., etc. Now, floating point branches, okay, BCLT, so branch on true and branch on false. So it is the status of the coprocessor from CXSD. So you first need to do a comparison instruction, C equals this, and then, so it doesn't have something like BNE, BLE, BGE, that kind of thing. It has BCLT and BCLF. So branching comparison true and branching comparison false, which is a status out of the last comparison instruction computed. So for the Mips coprocessor, there are 32 separate coprocessor registers. Okay, they are designated as F0 to F31. You can access them in your assembly program. Double precision instruction .d can only access register with the even index. So it can access register F0, double precision instructions, right? F0, F2, F4, F6, etc. Why? Because it is double precision, but each F registers are 32-bit. That means a double precision instruction need, in order to access 64-bit, it need to access 2 registers at a time. Okay, so if double precision instruction accessing F0, that means it is accessing both F0 and F1. They are together. That's why they are not allowed to access F1. Their access to allowed next is F2. So they can access F0, they can access F2 where it will access F2, F3, then it can access F4 where they will access both F4, F5 and so on and so forth. So even odd pair makes a double precision number in this case. Now there are separate load and store instruction. Load C1, which means load word into coprocessor 1, load word into coprocessor 2, etc., etc.